we've been exploring different ways to represent motion effectively, right? We've been exploring dot diagrams, we looked at numerical representations, I showed you different types of diagrammatic representations, so I really looked at different paths you could take. I've showed you many ways, but today we are going to be looking at a very important way we represent motion and most data in science. So today we are going to be exploring position time graphs. And I will be calling these just PT graphs in your notes because save some space. So this is a graph that plots an object's position versus time. So it plots an object's position versus time. Let's see what you remember from graphing in previous years. Which is my x and which is my y? You got it if you would. What's my x? It's the horizontal, right? Is my x. And the vertical is my y. You may have heard these referred to as your rise and your run at some point. Have you guys heard those terms before? Rise and run? Yeah. Yes? All right, good. Does anybody know what else we call our y? There's a different name for it. Typically, is y the thing that we measure when we do science experiments? Yes or no question?
Yes.
Yes, good job, yes. We also call this the dependent variable. So your dependent variable, which is my y, it depends upon my independent variable. This is the thing you measure, right? This is the thing you measure, and it will depend upon your independent variable. Depends on my independent variable. Now, my independent variable is my x, and it's independent of my y. My independent variable is independent of my dependent variable. Now, this is the thing that you kind of set during your experiment. So this is what you control. This is the thing you control. That's kind of my non-sciencey way of saying it. So when we talk about a position time graph, your y variable will be represented by your position, and your x variable, your independent variable, will be represented by your time. Now, next class, we are going to be doing a lab where we are going to be creating position time graphs. So we are going to be taking beanbags and we're going to be dropping them. What do you think remains constant during that experiment? What do you think remains constant? When am I going to be dropping my beanbags? It'll be a constant time interval. So every second, I think, is what we're going to do for the beanbags. And then we're going to plot out your change in position, giving some changing variables, like changing your speed, or accelerating or decelerating. So that's just the really basic graphing stuff out of the way. Let's actually make some graphs now. Let's make some graphs. Alright, let's say, by the way, when you were plotting points on a graph, how are they often given to you? Have you guys ever heard the term ordered pair before? Michael Shake said yes. If I gave you a pair of numbers, which number represents your x, which represents your y? Yeah. Yeah, when you're given an ordered pair, it would have looked like this, right? Your x, your y. We are now going to create a set of ordered pairs with our position time data. Now, let's just keep it really, really simple. Now, hilariously, I actually made the same mistake I did last class. I actually stole the ruler from this class. I will be right back. What I want you to do is I want you to plot these ordered pairs on a position time graph. Okay, so plot these ordered pairs on the position time graph, and I want you to tell me what the velocity of this object is. Who can tell me the velocity of this object? You should be able to just tell by looking at it.
1 meter per second.
Yeah, you got it, Vicky. What is it?
1 meter per second.
How do you know it's 1 meter per second?
Because it increases every 1 meter increases per second.
Reverse that thinking. For every second, you increase your position, your change in position by 1 meter, right? For every second, you move 1 meter. So if you plot these points out, right, if you plot these points out, what did you find when you plotted them out? How would you describe these points? If I were to draw a line through them, what kind of line would it be?
Linear.
Yeah, it should be a straight line. Of course, I just eyeballed this, so it's not going to be absolutely perfect. But you're right, it should be linear. It should be effectively a straight line. It should go through the zero. So it should be a straight line that goes through 0, 0 in this case. Now, you are right, my velocity is 1 meter per second. But if I wanted to figure this out mathematically, how would I do that? What is my velocity formula? Yeah? Yeah, it's going to be your change in your position, aka your displacement, over your change in time. Over your change in time. Now, how do we measure a change in something?
Final subtract initial.
Yeah, it's going to be your final position, subtract your initial position, over your final time minus your initial time. Now, we could choose 2 arbitrary points. It doesn't matter which 2 we pick on our table of values. We could choose time 4 seconds and time 2 seconds, for example. Now, if I choose time 4 seconds and time 2 seconds, we're going to see that I get 1 meter per second. So at time 4, my displacement is 4 meters. At time 2, my displacement is 2 meters. At time 4, well, clearly my time is 4 seconds. Time 2, it's 2 seconds. This gives us 2 divided by 2, which is equal to 1 meter per second. Now, we're going to get to a really important part here of this unit. And that is slope. Anybody here remember the formula for slope? You should have learned it last year. You should have learned it last year. Sabir?
Is it y2 minus y1 divided by x2?
Excellent. And there's a simpler way of saying that, though. You may have heard it said, well, it is the change in your rise over the change in your run. It is the change in your rise over the change in your run. And then Sabir, you're right. How do we measure the change in something? Well, that was y2 minus y1, aka your final minus initial, and your x2 minus x1. And when you were asked to find the slope, you were asked to pick two ordered pairs from your graph. At least you should have been. So let's pick two ordered pairs. Let's pick this point here. What is my ordered pair at this point? What is my x and y value at this point? This one right here. Yeah, it's 4 and 4, right? My x value is 4, my y value is 4. What is my ordered pair at that point right there? 2 and 2. So if I chose these two ordered pairs, by the way, on a straight line, does it matter which points I pick? No. If I choose any 2 points on this line, will it give us the same answer?
Yes.
Yes, it will. Keep in mind that your second point is always the point that's further down this way on your graph. So y2 minus y1, well, we have 4 minus 2. And what is our y-axis? What's the unit of our y-axis?
Meter.
It's meters. So we have 4 meters minus 2 meters. Then we have our x values. We have 4 minus 2. And what is the unit on our x-axis? It is seconds. So we have 4 seconds minus 2 seconds. So again, this is going to be equal to 2 meters over 2 seconds. And we get an answer of 1 meter per second. So what can you say about the slope of a line for position time graphs? What can you say? Well, look, we got the same answer here, right? That is our what?
Velocity.
So what can you say of the slope of a line on a position time graph? What is it equal to? Ah, excellent. Who said that? Ailey, yes. What is it equal to? It is equal to your velocity. And this is an absolutely essential point. So write this down. Big asterisk. The slope on a PT graph is equal to your velocity. Your slope is your velocity, right? Your slope is your velocity. It is the same formula, right? We have the change in our rise over the change in our run. Well, what did we do here? We have the change in our position. Well, is our position our rise? Is it our y value? Is it? Is our rise our change in position? Yes, it is, right? That is our y value. Our run, is that the change in our time?
Yes.
Yeah, it is, right? So our slope is our velocity. That is an essential point to understanding graphs in physics. So on a PT graph, our slope is our velocity. So let's do another example. Actually, no, let's do some conceptual problems here. I'm just going to erase these numbers. Let's just erase the numbers here, erase this line. And let's explore some different slopes. Let's explore some different slopes. So same thing, this is going to be a position versus time graph. And let's say we had 3 different objects and we're plotting them all on the same graph together. So let's say we had object A here. Let's say we had object B here. And let's say we had object C here. So we have our 3 objects and we've plotted them all on the same graph together. Which of these objects is traveling the fastest?
A,
Why A?
because it's gone up higher in a shorter amount of time.
Excellent. So when you're talking about slope, you feel free to use the same definitions you would use in your everyday life, the same terminology. So if you were climbing a hill and it was like this, what would you say?
It's a steep hill.
It's a steep hill, right? So A here is a steep slope. In fact, the steeper your slope, the faster you're going. Which of my objects here is traveling the slowest? Why C?
Because it's like the same time as B.
The same time as B?
Well, like,
You're right, it is the slowest. So this is your fastest, right? A is your fastest, and C is my slowest. Why is C my slowest? What would you say of a hill that has like a slope like this?
another hill.
What's that? Would you say, yeah, Haley?
Like he's moving the same speed as B, but on a less steep slope, so it's less.
They're not moving the same speed. They're moving different speeds, right? This one's moving slower than this one, but the rest of your explanation is correct, right? C has a lower slope. It's a more gradual slope, right? Versus A, which is like this. So, if I wanted to show you this mathematically, looking at this graph, all we have to do is this. We can draw a straight line up from any time point. Right, so here's some time. It doesn't really matter what the time is. There's some time. And we can see that at this time, which of our objects had the greatest change in position?
A.
It was A, right? If we trace this to our x-axis, right? If we trace this across to our x-axis, we can see that A here clearly had the greatest change in position over the same amount of time, right? This is like, say, time 1 second, okay? After 1 second, C here has changed its position that much. B has changed its position that much, right? C has changed its position that, or I screwed those up. So it's C's changed it this much, B's this much, A has changed it that much, right? So A is going the fastest, and again, you can tell just by looking at the slope. The steeper the slope, the greater your change in position over time, right? The greater your change in your rise over the change in your run. And the greater your change in your rise versus the change in your run, the faster your velocity. Because slope is equal to what? Your slope is your?
Velocity.
It is your velocity. Does that make sense? Yes, the slope is your velocity. So the steeper the line, the greater the velocity. Let's look at a different example. Let's say I drew let's say a straight horizontal line. Let's just say I drew a line that looks like this. What would you say of that object? What would you say of that object? in math, what does a horizontal line tell you? What's the slope of this line?
Doesn't have one.
Doesn't have one. Do we have a change in our rise?
No.
No. Your slope is 0, so what's my velocity?
0.
0. So what does that tell you about this object?
It's not moving.
Oh, good job, Josh. It is not moving, right? This object is not moving. So, if you have a horizontal line, your object is not moving at all. So let's explore slope now, just very much non-mathematically. The more horizontal your line, right? If I had a slope that was like this, and we started to decrease it, am I decreasing its speed? Yes. So the more horizontal your line becomes, the slower you are moving. In fact, if you go completely horizontal, what has your object done?
Stop.
It's come to a stop. Now, in the opposite sense, the steeper my line becomes, what's happening? Yeah, I am increasing my speed. I'm going faster and faster. So keep that in mind as we do our next example here. So let's look at another table of values. Let's say we have a table of values that looks like this. Might as well use the same example as this morning. So this object here, what can you tell me just by looking at its change in position versus time? What can you tell me?
It's times itself.
What is it, sorry?
Times itself.
What do you mean times itself?
Like every, like 2 times 2 equals 4. It's true.
You're overthinking it there, Abby. You're overthinking it. What can you tell by looking at your change in position data?
It's not linear.
Yeah, it's not linear. How can you tell that? How did you come to that conclusion?
The distance doesn't change like at an equal rate.
Correct. So you'll notice that for every second that goes by, from here to here, how much did we increase our distance by?
1 meter.
Our position. 1 meter. How from here to here?
30.
3. And then
5.
5, and then 7, right? So for every second that goes by, we are increasing the distance that we cover. So what is our object doing? Practical terms. What is it doing? Sabir?
Speeding up.
Yeah, excellent. It is speeding up. Our object here is speeding up. Now let's plot that on a graph and let's see what this looks like. So I'm going to try to make this one a little more accurate than last month's. So let's go like that. That's 1, 2, 3, and 4. And now we have to go all the way up to 16 here. So 1, 2, 3, 4, 5, 6, 10, 11, 13, 14, 15, and 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so our first point is at 1 and 1. So it's way the heck down here. My second point, if I plot it out, is at 2 and 4. My third point is at 9 and 3. And my fourth point is at 16 and 4, something like that. Now, what would happen if I tried to draw a straight line through these points? Could I do it? Not really, no, right? It would not look pretty. It would not overlap with my points at all. So we're going to draw a curved line of best fit. So if I were to draw my line of best fit here, my curved line of best fit, it would probably look something like that. Now, what do you notice about this object? What do you notice about this line? It curves. It curves. How is our slope initially? Is it like low or is it steep? It's pretty low. And what happens over time?
It's steeper and
It's getting steeper and steeper. So what's happening to our velocity? It's getting faster and faster. So if I were to tell you, I don't expect you to know how to calculate this, by the way. This is more of a grade 11 thing. But if I told you your velocities, this is what they are. This is what they are. So those are your velocities. So what is the acceleration of this object? You can tell just by looking at these numbers.
2 meters
You're right, yeah. What's the unit? So it's 2 meters.
seconds squared.
Yes, that is 2 meters per second squared. So our object is accelerating at a rate of 2 meters per second squared. We are speeding up. We are speeding up. So let's now talk about the different types of lines you can get. So let's put another big asterisk here. So when we're talking about slope on a PT graph, what does a straight line represent? What does that tell us in regards to our velocity? Ooh, excellent. That will be a constant velocity. So this is going to be a constant velocity. If our line is straight, it is a constant velocity. Because is the slope on a straight line the same everywhere? It is, right? It is. If you have a straight line, it doesn't matter which 2 points you pick to calculate your slope, because it's the same everywhere on that line. Your velocity is constant. Now, what if I had a horizontal line? Straight horizontal. What does that tell us? It is not moving. You still have a constant velocity, by the way, because it's a straight line, but what is your velocity if it's a horizontal line? Well, it's not moving, so what's your velocity? It's 0, right? If your line is horizontal, it is 0. So your horizontal line will represent an object that is at rest. That is the sciencey way of saying that it is not moving. And then lastly, what does a curved line tell us?
It's getting faster.
Not necessarily. Not necessarily. I'm going to show you an example right away where that's not necessarily true. What does a curved line tell us?
Change in velocity.
It has a change in velocity. Excellent. So your velocity is changing because if I have a curved line, is my slope changing? Right? Is my slope changing? Of course, right? So my slope is changing, thus my velocity is changing. And by definition, that means that if you have a changing velocity, this means that you have an acceleration. So you changing velocity, therefore, have an acceleration. And this doesn't necessarily mean it's speeding up. It could also mean it's slowing down. And I'll show you what I mean by that, Ippy. So let's say instead, my line looked like this. Let's say instead my line looked like that. What is happening to my slope here? Do I start out steep or with a gradual low slope? It's pretty steep, and what's happening?
Slowing down.
I'm slowing down. So every single time your slope starts to look more horizontal, your object is slowing down, right? Because once my slope is completely horizontal, what does that mean? Yeah, my object isn't moving, it's at rest, right? So the steeper my slope becomes, the faster I'm moving, and the more horizontal it becomes, the slower my object is moving. But this doesn't necessarily always have to look like this either. We could have situations where we are moving in the opposite direction, because in this unit, we are going to be exploring objects that are moving in effectively one dimension. You know, east, west, left, right, up, down. So we are going to be exploring things that not only travel east, but also travel west. So what if I instead had an object that was traveling, let's say, like this? Let's do that same example again. We have three objects here. Right, this is A, B, and C. Which of these objects is traveling the fastest? Excellent, Iffy. We are now moving in the opposite direction. Right? Our slope, is it positive or negative now? Our slope is negative. Right? If I were to calculate, I can choose any two arbitrary points, like here and here. Right? If we did the change in our rise, that's your y2 minus y1. Well, you'll notice that here my point is, say, a value of 2, and here my point is a value of 10. Well, which one is my y2? I'm showing you mathematically that it's going to be negative, but what is my y2? Yeah, it's the one that's further this way. So really this would be 2 minus 10, which is negative 8. So if your slope goes from this to this, now you have a negative slope. Now you are moving in the opposite direction. And you are right, Ippy. A is traveling the fastest. How do you know that A is traveling the fastest? It's for the same reason as before. How do you know that A is traveling the fastest? Sorry, what did you say, Haley? Yeah, the slope is steeper, right? The more horizontal your slope becomes, the slower you are moving. And I could do the same activity where I draw this line up, right, at any time point, and you can see that we cover a greater change of position with A than with C. So A is not moving the fastest, C is moving the slowest. We are just looking at our object moving in the opposite direction. And in that same vein, I could draw curved lines. I could draw curved lines. I could draw lines that look like this, for example. What is that object doing? Is it slowing down or speeding up? What do you guys think? Is it slowing down or speeding up? Does everyone agree? Oh, you guys are good. Yeah, most of you nodded your head there. You're right. It is, in fact, slowing down. How can I tell? Well, what's happening to my slope? It's getting more horizontal. Therefore, we are slowing down. How about instead if I drew something that looks like this? What's that object doing? How do you know it's speeding up? How do you know it's speeding up? Your slope is becoming less horizontal. It is becoming steeper. So I know contorting in your mind and thinking in the opposite direction is hard for most students, which is why this is going to take some practice. This will take some practice. Let's finish today by looking at a rather complex example. Alright, let's say, for example, you had an object. Right, this is the positive direction, this is the negative direction. Because again, 0 is just some arbitrary point, by the way. I could say that this eraser is 0. Right? Everything in this direction is positive, everything in this direction is negative. 0 is just some arbitrary point. It'll become much more relevant when we talk about velocity time graphs. But right now, there's no 0. It's not super important on your position time graph. It's important if I ask you, hey, where does your object end up? But in terms of which direction the object is moving, is it speeding up, slowing down? That 0 point plays absolutely no role in that. All right. That looks pretty good. Let's say this is going to be A, B, C, D, E, F, G, and H. Now I'm going to give you a minute right now. What I want you to do at each of these points here, I want you to describe from A to B, what is my velocity and what is my acceleration? Okay, and I don't expect you to write down a magnitude here. I want you to list, do I have constant velocity? Do I have changing velocity? Is my velocity positive, negative? Is my acceleration positive, negative? Do I have no acceleration? Again, you don't need to write down magnitudes here. You're just talking about direction and is it constant or not. So take a minute, try to plot out. I'll help you with the first one actually. What's happening from A to B? It's not getting faster. Constant velocity. How do we know it has a constant velocity? Yeah. Because it's linear, it's a straight line, right? Our slope is not changing, therefore our velocity is not changing. So here, from A to B, we have a constant positive, right? We have a constant positive velocity. Do we have an acceleration? No, right? Because our velocity is not changing, so our acceleration is 0. So take a minute, try to figure out the other points on this graph. All right, someone tell me what's happening from B to C. For this block right here, what is this object doing? Yeah, you're right, it's at rest, right? This object is not moving. So what would my velocity be? 0. Right, we're not moving, we're just stopped. From C to D, what is happening? Now this is a really important point that I forgot to write down previously. On a position time graph, when does your object change directions? On a PT graph, the object changes directions when the slope changes from positive to negative and vice versa. So at C to D, is my object now traveling in the opposite direction?
Yes.
Correct. Right? From A to B, if this was my 0 point here, and this is the positive direction. From A to B, I'm moving at a constant positive velocity. I stop for a little while. And then from C to D, I am now moving at a constant negative velocity, right? I'm moving in the opposite direction. So here we have a constant negative velocity. And if my velocity is constant, do I have an acceleration?
So,
No. As I walked around, I noticed a lot of you here said that our object was speeding up. It was not, right? Our slope wasn't changing, therefore our velocity wasn't changing. How about from D to E? What is happening there? Yeah, we are speeding up in which direction?
Positive.
Yeah, we are moving in the positive direction and we are speeding up. So we have a positive velocity, and what is our acceleration, positive or negative? Yeah. What's the general rule again? If you are speeding up, my velocity and my acceleration, are the directions the same or the opposite? They are the same. If you are speeding up, your acceleration has the same direction as your velocity, as the direction you are moving. So we have here positive acceleration. How about from E to F? What's happening? What's happening? Let's hear from Eddie. What do you think? Sabir?
I think we're part of it, it's actually,
Yeah, so I didn't draw this perfectly. I kind of wanted this to be like a straight line at this point right here. Like a completely straight line. So your slope is doing this. So what does that mean? You are slowing down. Is my object still traveling in the positive direction though?
yeah.
Yes. So we still have a positive velocity because my slope is still positive. But we are becoming more horizontal, so we are slowing down. So what is my acceleration then? Yeah, it's going to be in the opposite direction now, right? So if I am slowing down, my acceleration is in the opposite direction to my direction of motion. How about from F to G? We are speeding up in the negative direction. So we have a negative velocity. And what is our acceleration? Oh, good job, Amy. This is what really confuses students. So the general rule is if we're speeding up, is our velocity acceleration moving in the same direction? Yes. So you actually have a negative acceleration. You are speeding up in the negative direction, right? My slope is becoming steeper. And then lastly, G to H. Are we still moving in the negative direction? Is my slope still negative? Yes. So we have a negative velocity. And what is my acceleration? Am I slowing down or speeding up? Right, my slope is becoming more horizontal. I am slowing down. Oh, positive. Right, so it should be the opposite. So this is a positive acceleration. So I know that was a lot to take in, but these are all of the lines. Literally. These are all of the different lines you can get on a position time graph. If you master each of these, and you understand what's going on, you're going to do really good in this part of physics. By the way, I think this is probably the hardest part of this unit. So get to work. You can now do all of the position time graphing questions. And again, really important, if you don't understand something, what should you do? Ask, please. Please ask questions. All right.